Okay, gang, Kevin here. Welcome to another edition of Santa Rosa Junior College Wine Studies Online. Today we're talking about the stability of the conjugate base of an acid. Or in other words, why is tartaric acid a stronger acid than malic acid? So let's go back to where we were in class when we talked about the fact that tartaric acid has a lower pKa than malic acid. Tartaric acid, 2.89. and malic acid 3.40. So let me 2.89, 3.40. So we said that means tartaric acid is a stronger acid than is malic, and so the question we want to address today is why is that the case? So let's go first review what we talked about the other day. Remember, we talked about the fact that the conjugate base of tartaric acid is bitartrate. So here on the left is tartaric acid, and we often call that H2T because it has the two acidic protons still attached, and we pointed out that acidic protons are there and there. Over on the right is bitartrate, which is a species that results after tartaric has lost one proton. So that proton came off. This oxygen stays behind with a negative charge, and that species, bitartrate, we often call HT minus, one acidic proton still attached and a negative charge overall. That is the conjugate base of tartaric acid. All right, so the conjugate base is here, and the acid is here. And remember, we said that there's an equilibrium that gets set up that tells us how strong the acid is. And so there are two equations. We said if we take H2T, tartaric acid, if that loses a proton, it leaves behind bitartrate, HT minus. And remember, that proton gets picked up by water. So H2O plus the proton goes to H3O plus, and those are two half reactions. We'd sum those because they go together, and we'd have H2T plus H2O goes to HT minus plus H3O plus, right? So the protons on each side of the equation actually eliminate, and that leaves our full equation, the one here on the bottom. And then we set up an equilibrium, remember, where we said that the equilibrium constant, Ka in this case, because we're talking about the dissociation of an acid, so we call it Ka, and that equals to the concentration of the products, the product of the two concentrations of the products divided by the concentration of the two reactants. And you may remember from chemistry that you would raise these concentrations to some exponents if we had coefficients in front of the individual species that were different than 1. But here in this equation they're all 1. So we could write in the little ones as exponents, but we don't bother to do so. All right, so if you had to go back to general chemistry, you'd remember those exponents. But that's our equation. And remember then we said that if you have if you take the Ka for tartaric acid, it's fairly small. So we take the log of that, and we define then pKa as minus the log of Ka. And we said then that a stronger acid means you have more product, right? More of these species at the top. So what that means is you have a Ka that's larger. So minus the log of that actually is a smaller number. So a smaller pKa means an acid is stronger. Right, so let's go and if we go on then from bitartrate to how it becomes tartrate, we can, if we took the equilibrium here between these two species, in this case, if you look at this pair, the acid is bitartrate, and the conjugate base then is tartrate, right? It's because, again, we've lost an acidic proton. We end up with that negatively charged oxygen right there, right? So for this pair, bitartrate's the acid, tartrate's the conjugate base. If we take, let's surround the other pair in red, in that case, tartaric acid is the acid and bitartrate is the conjugate base. We said the pKa is 2.89 for the loss of that first proton. All right, so it's that proton there that comes off right there, and that has a pKa of 2.89, that equilibrium between tartaric acid and bitartrate. Then we also have an equilibrium clearly between bitartrate and tartrate, and that has a separate pKa, and the pKa for that separate, the loss of that second proton is 4.40. So what does that mean? Well, it means that bitartrate is a weaker acid than tartrate. Tartrate loses that first acidic proton, the one that's right there, with a pKa of 2.89. So it's a moderate acid, fairly weak, not too strong. But bitartrate loses its second proton, again the one right there, the second acidic proton. Bitartrate loses that one with a pKa of 4.40. So that one doesn't come off as readily as the first one. So oftentimes when you see acids, in this case we know that tartaric acid has two acidic protons. When you see acids listed, they will show, in this case, two pKa's, one for the first proton, one for the second proton. First proton 2.89, second proton comes off not as readily, 4.40. Okay, so that's tartaric. Let's go to malic. Malic has similar species. We start with malic acid over here on the left. And remember we said there are two acidic protons in malic acid as well, so these two. And when the first one comes off, it forms bimalate. So similar, just like we saw with tartaric, there's that negatively charged oxygen that results after the first proton. That guy comes off. And then bimalate can lose the other proton. Let's make it blue down here. So when that other proton comes off, you end up with malate, and you have the other negatively charged oxygen down there. All right, so same series as tartaric acid. The pKa's differ. Malic is 3.40 for the first proton to come off, and 5.10 for the second proton to come off. So tartaric was 2.89 for the first. Malic is 3.40 for the first. Tartaric was 4.40 for the second, and malic is 5.10 for the second. So for both protons, tartaric is a stronger acid than malic. All right, now we get to the crux of the matter. Why is that the case? So there are four structural effects that impact pKa. Four of the key ones that we're going to talk about. You would talk about these in detail in organic chemistry. We'll talk about two of them because they impact these two acids that we are concerned about. We're going to talk about resonance, and we're going to talk about induction. All right? So let's get to resonance. Resonance is largely why these two species are acidic in the first place. And one way to look at that is to look at an alcohol versus a carboxylic acid, right? So if you remember, an alcohol is just a molecule that has a hydroxyl group on it. The rest of the molecule is symbolized by R, right? So that's that guy. And a carboxylic acid has the structure like that, and that is your carboxyl group right there. All right. So we're looking at the acidity. We're comparing the acidity of these two protons, one on an alcohol and one on a carboxylic acid. If we look down here, we see I'm putting a box around the alcohol after it's lost its acidic proton. This is ethanol, right? CH3, there's a CH2 right there, and then the OH. And we've lost the H, so ethanol can lose its proton, but not very easily, because look how high that pKa is. pKa's of alcohols tend to be around 15 or 16. All right, so ethanol is around 16. Now, to the right, then we have the carboxylic acid, which is ethanoic acid. It's still ethanol, right? There are two carbons there and there. And here we show that the acidic proton has already come off of this position. And we draw a double bond to this oxygen here and a single bond to this oxygen and show it as negatively charged. But we can write a resonance structure, in other words, an equivalent structure that would have the double bond and single bonds that I'm circling in red here, have those positions reversed. So it turns out that what really happens in the molecular structure is there is a partial double bond to each oxygen. Instead of a double bond to one and a single bond to the other oxygen, there's a partial double bond to both. And it turns out you can do a lot of experiments to prove that that's actually what happens in reality. What that means for us is that negative charge that results from losing the proton, that negative charge is spread over this entire area. So instead of the negative charge being centered over here on the oxygen, it's spread over this entire area. And we said in class that's like trying to pick an apple off a tree. If the apple is right above you in a fixed position, easy to pick. If that apple is blowing in the wind and the leaves are the branches are moving around a lot, then that apple is sort of dispersed. Well, it's not sort of dispersed, it is dispersed over a wide area. Makes it harder to pick. Likewise, this species over here on the right, this species of ethanoic acid or acetic acid would be the common name for it. This species of acetic acid is much less reactive because that negative charge is spread over a large area. Look at ethanol. There's no resonance structure you can draw that'll move that negative charge out of that one position. Here the negative charge on the right moves around. In ethanol it doesn't move around. So ethanol is much more reactive because that negative charge is in one spot. And it'll react readily with any proton that comes along. It'll react and rejoin ethanol. That's why ethanol has a high pKa. It's not very acidic. It doesn't let go of that proton very easily. If it lets go of it temporarily, proton comes right back on and reacts. But in acetic acid or ethanoic acid, when that proton comes along, it's gone, it comes back, it's trying to find a place to react here, and it can't quite figure out where it's supposed to pick that apple. Thus, the conjugate base of acetic acid, which is acetate, has a much lower pKa, around 3 or 4 in fact, much lower pKa than ethanol. So that's why carboxylic acids are in fact acids. So that tells us why both tartaric and malic are acids, right? Because they have that same carboxylic acid structure. But why then is tartaric a stronger acid than malic? And that gets to the second structural effect, and that's inductive effect, and we're almost done here. Inductive effect is the redistribution of electron density through molecular sigma bonds. So an example would be if you had CH3COOH, acetic acid, versus CF3COOH. Let's look at those two species. The one on the right is acetate, right? It's acetic acid that's lost a proton. And we said that this negative charge is actually distributed over this whole area. pKa of acetic acid for losing that first proton is 4.76. So it's a moderately weak acid. It's weaker than tartaric acid. But look if we add 3 fluorines here. So on the left here is the same species, except that the 3 hydrogens at the end here have been replaced by 3 fluorines here on the left. Look where the pKa does, what the pKa does. It goes way down to 0.23. Why is that? Fluorine is very electronegative. It's the most electronegative atom on the periodic table. So if you remember back to chemistry, electronegativity is a measure of how much an atom will attract protons. And look at fluorine, it's the largest one, 4.1. It's double the electronegativity, and this is on the Linus Pauling electronegativity scale. It's double the electronegativity of hydrogen. So what that means to us, if we go back to our structures, is these fluorines are very electronegative. They're going to actually pull electron density toward themselves with a much stronger attraction than will hydrogen. Right? Hydrogen will pull some electron density toward itself, but fluorine will pull a lot more. Right? So where a hydrogen pulls some electron density away from this negative charge, fluorine pulls a lot more away from that negative charge. And what that does is then it further spreads that electron density over a bigger area. It makes the species on the left much less reactive, much less likely to pull a proton that comes in back toward it. Acetate is more likely to pull a protein back toward it. So that's acetate versus this fluorinated acetate. What about Malic and Tartaric? Well, look at those two structures. Bitartrate on the left, bimalate on the right. This negative charge here is distributed across this whole area here. Likewise at the top. Likewise for bimalate. Look at the corresponding structures. Tartaric acid has an oxygen here. So does malate. Tartaric acid also has an oxygen down here, where malate only has hydrogens at that position. Look at the relative electronegativity. Oxygen, 3.5 electronegativity on the Pauling scale versus hydrogen's 3. Oxygen's a lot more electronegative. So just like fluorine attracted electron density away from the negative charge here, the tartaric acid has 2 oxygens here which can attract electron density away from the negatively charged area at the end. Malate only has 1 oxygen. Thus malate is a little less stable in the presence of a proton, right? So the proton, if it has a little attraction here, for bimalate actually has less attraction, minor attraction for bitartrate, right? Strong attraction, the proton, for malate relative to tartrate. So malate has a higher pKa and is a weaker acid. And that, my friends, is why tartaric is stronger than malate. Hope that makes sense. Bring questions to class, and I will see you next time. Thanks.